Hey kids, Smath here. I'm going to intro chapter 18 for you this morning, and we're going to talk about reaction rates. Now, what exactly is a reaction rate? Well, this is going to be talking about the speed of a reaction. Chapter 18 is going to have three different topics for you. The first one of these we're going to talk about is rates. The second one's going to be equilibrium, how far to the right or left, how much to completion the reaction goes. And the third one is going to be thermodynamics 2. Will the reaction happen by itself? So these three topics are usually the advanced topics for first year, but they're really kind of cool topics because it says how fast is it going to go, how far is it going to go, and will it go by itself? So these are kind of cool. Now in this one, we're just talking about rates. And let me get this lined up. It's a little bit better. Rates are how long it takes for a reaction to occur. So in this case, we're going to measure things in terms of concentration of a reactant or product per time. Generally, this is going to be done in terms of molarity per second, or if we take molarity apart, it'll be written in terms of moles per liter seconds. All right. It could be in a different term. It could be in molarities per minute, per hour, per days. Generally, though, it's always going to be molarity. And for us, it's always going to be molarities per second because we want our reactions to go relatively fast. Now, this is the reaction rate, the speed of the reaction. What we're going to talk about later on in the chapter is spontaneity, this delta G. We're going to do those calculations towards the end of this series of videos. And this is that, will the reaction occur at all by itself? It doesn't talk about how fast. So these three topics that I'm laying out in these series of videos really do have to stand independently of each other, but they do kind of interact a little bit. We're going to show that interaction, that thread. So all we're worried about right now is speed. Will this occur? So right now, let's talk about why chemical reactions occur. And that's going to be based on something called collision theory. Now, for collision theory to work, we have to go on the assumption that atoms, ions, molecules, particles will react to form products when they collide. Now, that part's not all that important. We know that that happens. That's pretty normal. The important part is this second part right here that I'm highlighting, provided that they have sufficient kinetic energy and the correct orientation. Now, here's how I've always kind of understood and explained this. This is kind of like particles going to the demolition derby, the figure 8 demolition derby, and there are going to be collisions where the figure 8 crosses. Well, in order for the reaction to occur, there has to be a collision between particles, and it has to be sufficient enough that if we were at the demolition derby, it would knock that car out of the race. Those two cars would be spinning around, boom, they'd collide at the figure 8 and they would stay stuck together and they would both be knocked out of the race. They wouldn't be able to continue on anymore. So that's what's going on here. Is it also says we're looking for molecules to collide highly and with a lot of energy. And it also says that molecules will decompose with enough energy to break apart a bond. See, bonds are formed and molecules go to lower energy. And so to break those molecules apart, we would have to put energy in and that would decompose. So collision theory accounts for how things combine together. In our demolition derby example, they have to have sufficient collision and energy, and also in a decomposition way, in that those particles have to have enough energy put into the system to make them vibrate enough that they're going to break apart and they're going to decompose. So that's collision theory. Now, both processes are going to need energy. They're going to require energy. Now, this is called a reaction coordinate that we have right here. This is called a reaction coordinate. And what it does is it correlates the energy of a reaction to the progress of the reaction. Another way of saying progress is this would be time on the x-axis. And so we start with the reactants over here at time 0, and we go to the products to the right. How does it get there? That's what this chapter is about. This chapter is about how fast it gets there and how far it gets there. Does it go 100%? So in this case, we're worried about how fast. That's going to be the energy grid, this energy coordinate. Well, if we start at the reactants, there's a certain amount of energy that particles must have for this reaction to occur. And that amount of energy is called the activation energy. That's the energy needed to initiate or start a chemical reaction. And so once we've given enough energy to get up to the peak of this reaction, right there at the top, we're trying to get as many particles up to the peak of this reaction, then it goes and continues on to the products. Now, we just finished the unit on thermodynamics, delta H, the enthalpy. Well, that enthalpy is right here. That's the heat evolved during the reaction, is this delta H. And what that delta H is it's the difference in energy between the reactants and the products. So these energy coordinates are kind of important because when particles have just enough energy for the reaction, they create what's called an activated complex. These activated complexes, we will never write, we will never see them in a chemical equation because they're very unstable. Excuse me. They're very high energy, they're very unstable. And at that point, at the peak of that graph, they could go backwards and form back to the reactants, or they could go forwards and form the products. Now, at some point, these are called transition state. So activated complexes and transition states are the same. Intermediates are species that are going to be formed and consumed in a chemical reaction. Now that sounds kind of weird. What do you mean they're formed and consumed? Well, we're going to learn later on about mechanisms, and in mechanisms, we're going to make something in one step, and then in the next step of the mechanism, it's going to get consumed and used up to make something. Those are called the intermediates. Once again, we won't see them in the overall reaction, but we do see them in the mechanism that we're producing here. And so they're kind of cool from that standpoint. Now, for a few minutes, let's talk about factors that are going to affect the rate. Let's say we want something to go faster. Well, we could talk about the nature of the reactants. What we mean is some things are more reactive than others. And so if we wanted to burn something, we would get something like gasoline. Gasoline ignites very quickly, it goes very fast. Conversely, if we got something like oil, oils are also flammable, but they burn at a much slower rate. How come? Because they're different particles. That's what the nature of the reactants is. We can also talk about the concentration. The higher the concentration, usually the faster the reaction goes. If we put more stuff, we get a faster rate. Other things that affect the rate of the reaction here is particle size. If we want things to go faster, we need to increase the surface area. That's what we're talking about right here. Smaller particles react faster. The faster reaction rate. Something else that's a general rule of thumb, general rule is if we increase the temperature 10 kelvins, we will double the rate. And so if we go from 298 to 308 kelvins, 25 to 35 degrees, that's going to double the speed of the reaction. It's going to go twice as fast. How come? Because by putting more energy in that 10 degrees, that 10 kelvins, by putting more energy in, those particles are moving faster. And the more movement, the more collisions, more they have the activation energy, and life is good. So those are our factors: particle size, temperature, concentration, also the nature of what it is. Now, with that being said, let's talk about catalysis. Catalysts, we learned about these in biology. Enzymes are catalysts, right? What do these catalysts do? They lower the activation energy. So if we were to look at our graph, at our little reaction coordinate that we had earlier, it would look like that. Well, if we catalyzed it, it would look like that. The red is the catalyzed version. The yellow is uncatalyzed. What does that mean? When we put a catalyst in, when we use those biological enzymes lower the activation energy. And by lowering the activation energy, guess what? More particles can have that energy easier, and they're going to react faster. Okay? Now, there are also things that are called inhibitors. And inhibitors actually do the opposite. The inhibited pathway is going to have a higher activation energy. It's going to slow things down. When do we want to slow things down? These two examples are really key. Nuclear reactions, we want to control. We want those to go slowly. And of course, food reactions. If I'm cooking cookies, I want them cooked at 350 degrees. I don't want to crank the oven up to 500 degrees. Hey, I'm going to make it go faster. Guess what? It's going to go so fast, I can't control that reaction. So sometimes we need inhibitors. In this case, the one I use for cookies, temperature. Okay, now there are two kinds of catalysts we want to keep track of. There are homogeneous catalysts and heterogeneous catalysts. We're right down here. Homogeneous are in the same state as the reactants. These are the enzymes that we talked about in biology. Heterogeneous, these are different states of matter. These are things like catalytic converters that contain heavy metals of palladium and platinum, and those react with our exhaust fumes to create CO2, nitrogen, and water vapor. They clean up our exhaust systems, okay? Now, let's come back and talk about our temperature and each of these individually. Temperature, usually increasing the temperature increases the reaction rate. How come? Because if we look at the number of particles on the Y and the amount of energy, if we increase the temperature, then we're going to say that here's where the activation energy is. Well, if we can put more temperature into this, we can shift this whole graph this way, and more particles will have that kinetic energy. We're going to move more of those particles to this area under the curve. So that's why. What about concentration? How come increasing? We've already explained this. Increase the concentration, increase the collisions, more reactions. And what about particle size? If I break up the particles into smaller, here's one big chunk of particles. If we break those particles up, now there's more interaction with the other particles, and that reaction can occur. Same thing happens here. If you have a big chunk of solid, it's only going to react on the surface. And so what do? We break it up into smaller particles, and now there's more surface area and there's more reaction. Okay, we've already talked about catalysts and catalyzed pathways. We've talked about inhibitors. And I think that gets us through our intro of this reaction, that this is going to help us with the basics of reaction rates, why things go the speed they go. I'm Smath. I hope this video helped you.